Alright, so this next chapter will be over thermochemistry. This is kind of, well, I think it's a fun one. You might not think so. But this is sort of a good introduction to thermochemistry. And basically we'll talk about what exactly is thermochemistry, and we'll kind of briefly show the applications. We'll go over some of the applications. And then in 1412, you'll really dig deeper into this, depending on who your teacher is. So this is a chapter where you really need to get familiar with a calculator. Thermochemistry is one of the extremely math-heavy topics in chemistry. So we will do a lot of calculations in this chapter, and you'll either really like that or maybe not so much. But let's just dig straight into it. Okay. So thermodynamics essentially is science talking about energy. Okay, so when we talk about how energy is transferred or energy is conveyed or used, okay, this is how we're going to talk about it. And this first slide is just sort of setting up, depending on who you would talk to, okay, they're going to tell you something a little bit different. Okay, so the first thing we're going to say is that energy is a dynamic quantity, or quality, I should say. Okay, and the reason I say that, okay, so to a physicist, energy, they would maybe say, is the ability to affect change. Okay, I don't know if I can play this. Okay, it looks like the 365 version won't play these. But basically what you see is the truck should roll across the screen, and eventually the brakes will get applied, and the truck will stop. Okay, so the truck has some momentum and some velocity, okay, moving forward. So some velocity, say 10 meters per second, moving forward. Okay, and then we apply the brakes, and the brakes stop the truck. Okay, so there's the energy change there. So something is affecting change. Okay, and that change is to, of course, stop the truck. Okay, so that's maybe if you talk to a physicist. Okay, so if you talk to a biologist, they would say energy is responsible for growth and for the development of organisms. Okay, so here we just see a seed germinating and eventually becoming a plant. Sure, great. So the plant uses photosynthesis to make energy and to grow itself and to maybe grow some sort of fruit or green beans or whatever it is. Okay, so that would maybe be how a biologist looked at it, and that could be in terms of a cell, could be in terms of an organism or a body. Okay, but now to a chemist, we might say energy is the ability to do work, and what work? Well, that's that could be variable, okay, or to transfer heat. So those two things, to a chemist, this is what thermodynamics is. Okay, so we have some thermal energy. Okay, so thermal energy, in other words, heat, okay, is going to affect another system. So here we have let me go back. So we have some sort of vessel with maybe a chemical reaction inside of it, and we have a fire that's putting energy into that system, and maybe now that system has more or less, maybe it has more chemical energy, and maybe it can do some reaction or do some work. Okay, so let's dig deeper into this. Okay, so the basics of thermodynamics is essentially the transfer of energy. Okay, so this can be in the terms of heat, which is this first example we'll look at. Okay, so here we have this idea that adding heat, so in this first example, so we have some molecules, maybe a gas. So the last chapter we talked a lot about gases and how a temperature affects them. Okay, so we have some gas molecules or some molecules in motion at some temperature. We add heat, and what do? We see that the molecular motion is faster. Maybe it's a gas that bounces around faster. Okay, so we're adding heat, but what are we really doing here? We're adding energy. Okay, so energy in the form of heat is associated with molecular motion. So exactly what I said. So if we put heat into the system, okay, we're actually putting in energy. Okay, so remember we talked about kinetic energy and all these things in the last chapter in terms of gases. Well, here, now we're just kind of digging deeper into that. So if we put in heat, we're really putting in energy. That's kind of the point I'm trying to make. Okay, but energy can also be transferred as heat until thermal equilibrium is established. Okay, and we call this change delta T. So anytime we see a delta here or in any other chapter, a delta means the change in. Okay, so we'll go over exactly how to calculate that in just a little bit. Okay, but just know that the delta means a change in. Okay, so change in temperature, in other words, a delta T, measures energy transfer. And up here at the top, I have sort of two bodies connected with a third body. So maybe this is like two pieces of metal, two blocks of metal connected by a third block of metal, something like that. Okay, but the point is if we heat up the one on the left, okay, so it has a lot of thermal energy. Okay, what's going to happen is if they're connected in this way, heat will flow towards the cold block. Okay, notice I didn't say that the cold would flow towards the hot block. That's not what's going to happen. Okay, so you can't transfer the lack of something. So this is the point I'm trying to make here. So you can't transfer the lack of something. In other words, heat is the idea of having more energy. So if I have, or just having energy in general. So if I have energy, and I guess what I said was correct. So having more energy, in other words, having more energy compared to the quote-unquote cold object. So what will happen there is the heat will transfer from the hot object to the cold object, and never the other way around. The example I always like to give of this is that when you, for instance, put ice in a glass and pour a drink on the glass. So our assumption is the ice made the drink cold. But what's actually happening is that the drink is transferring energy to the ice. Okay, so the drink is melting the ice. The ice isn't chilling the drink really. Okay, so just remember, heat is transferred, but you can't transfer the opposite or the absence of something. Okay, so cold doesn't transfer. Okay, so when we talk about thermodynamics, we're going to talk about science of energy and the energy transfer as heat specifically. And we're going to call heat lowercase q. So anytime in this chapter we see a lowercase q, know that we're talking about heat. Okay, so when we study thermo, what are we really studying? We're studying the transfer of energy as heat. Okay, so all thermodynamics depends on the law of conservation of energy, which is the first law of thermodynamics. So never forget that. If anybody asks you, your mom or your dad or teacher 10 years from now, asks you the first law of thermodynamics, or your friend even, say, hey, I learned something cool. You know what the first law of thermodynamics is? It's conservation of energy. And it's just like what we learned about conservation of mass. Okay, so you can't create or destroy matter. Well, here it's the same thing. We can't create or destroy energy. Okay. So we're going to talk about energy in a couple different forms. These first two, we have potential energy and we have kinetic energy. Okay, so potential energy is associated with stored energy. Okay, so here we have the example of a boulder, and you've probably seen this before in either a high school science class, or if you've taken physics, you've probably seen this analogy before. Okay, it's the same definition essentially. Okay, so potential energy is stored energy. Okay, so a motionless body has energy by virtue of its position. So sometimes we also call potential energy positional energy. I've heard that term before. Or the energy of position. Okay, maybe you've heard that before. The important thing here, though, is so it's stored energy. So it's potential because it could be. Okay, so here we have a boulder, and it's sitting at the top of the hill. And if we were to just give it a little push, it would roll down the hill. Okay. So now it's transferring the energy it had stored up based on the virtue of its position. Now it's turning that into kinetic energy. Okay, in other words, kinetic energy, energy of motion. Okay, so it's transferring potential energy into kinetic energy. That's why it's potential energy, because we can transfer it into kinetic energy. Okay, and as it goes down and down and down, sort of it's losing potential energy, gaining kinetic energy the longer it goes. Okay, and maybe if you're standing here, it's really going to transfer all that kinetic energy to you. Okay, but the point is, so the fact that it's high in the air on this hill is what gives it this potential energy. So potential energy is mgh, mass times gravity times height, just like you talk about in physics. Okay, so because it's up high on the hill and can be pushed, okay, then it has potential energy. The second thing is kinetic energy. Okay, so if I have the same physics definition, 1/2 mass times velocity squared. Okay, so as it's rolling, it has a mass, it's gaining velocity. Okay, so therefore it has kinetic energy. Bigger the mass, higher the velocity, more energy it has. Okay, but understand that we're transferring energy. So just remember that we can transform energy from potential to kinetic. Okay, another way we can do this is the example of pushing a spring down. So this would be mechanical potential energy. So we know that a spring works because, well, there's two types of springs, but this particular type of spring works because it doesn't like to be compressed. Okay, so it has more energy in that compressed state. Okay, so how is that energy? What kind of energy is it? It's potential energy because it's based on the virtue that it's being compressed. If we take a ball and we push the spring down and we let it go, okay, now the spring wants to go back to normal, okay, and it transfers that energy from potential energy to kinetic energy that it puts into the ball. Okay, so those were sort of setting up where we're going. Okay, now let's talk about some units. So the first unit will be the calorie, which is equal to the heat required to raise the temperature of 1 gram of water by 1 degree C. So a calorie, enough energy, or how much heat is required to raise the temperature of 1 gram of water by 1 degree C. Then we have 1 calorie is equal to a 1 kilocalorie, in other words, a kcal. You'll see this unit a lot, but it's just what it is. So it's a kilocalorie, so it's 1,000 calories, just like kilometers, 1,000 meters, same thing. Okay, and then if we ever see the food calorie, this is equal to 1 kilocalorie, or 1 kcal. Okay, and notice a big difference here. So when we're talking about energy calories, so normal calories, we're talking about little c calories, so little c cal. That's how we abbreviate this. If we're talking about food calories, it's always going to be big C calorie. Okay, so hopefully you can just try to remember that if it's a little c calorie, we're talking about a unit of energy. If we're talking about a big C calorie, this is when we're talking about something like food. Okay, so the last unit we'll talk about, or one of the last units, is the joule. Okay, so this is a big unit used in energy or in thermo. Okay, and 1 calorie is equal to 4.184 joules. And I promise you won't have to try to memorize that. It will happen based on how many problems you'll work out with this. Okay, so remember 1 calorie is equal to 4.184 joules. Okay, so if we add potential and kinetic energy together, we get what's called internal energy. And we represent this with an uppercase U, a big U. Okay, so internal energy of a chemical system depends on the number of particles, the type of particles, and the temperature. Okay, the number of particles is just how many do we have. So if they all have some kinetic energy, well, if we have more of them, okay, we're going to have more internal energy. What type of particles that is. So how heavy are they? How responsive are they to temperature? Okay, so if they're heavier, maybe they have if they have a bigger mass, maybe they have more energy, something like that. And of course, temperature. So if we increase the temperature, we know we're putting energy in. Okay, so the higher the temperature, the higher the internal energy of a chemical system. And changes in temperature, delta T, remember, are used to monitor changes in delta U. Okay, so if we want to know how much my internal energy has changed, we're going to look at the change in temperature. Okay, and we're going to see that throughout the chapter where we're using temperature as a probe for energy. Okay, so we can also define internal energy, delta U, so the change in internal energy, is equal to Q, which is heat, remember, plus work, little w. Okay, so anytime we see little w, that's going to be work, or in other words, P times delta V, so pressure times the change in volume. So work under standard conditions is constant. And under constant pressure, delta U is equal to Q. For the W, in other words, P times delta V, component falls out. Okay, so what's that saying is, so under constant pressure, okay, so if I have constant pressure, okay, then we're going to say that delta U is just equal to Q. Okay, because we're going to drop out this work term. Okay, don't worry about so much of the mathematics of it. Just try to follow me. Stay with me. Okay, so then Q is equal to, and the little p means at constant pressure, so then Q is equal to delta H, where delta H is the change in enthalpy. So enthalpy. And we'll get to exactly what enthalpy is in just a second. Okay, so I can say delta U is equal to delta H plus W. Okay, so W is still work, but understand that work by the system is usually small. Okay, so we can usually kind of forget about it. It doesn't affect things. It's so small that it doesn't really matter. Okay, so the energy transferred is mostly due to the heat. So I can say that changes in U, okay, so internal energy, are basically equal to delta H. Okay, so don't worry about so much where it comes from or the derivative, but just see that it is coming from some mathematical derivatives here. Okay, but the main thing to know is that changes in internal energy are equal to changes in delta H. Okay, or in other words, enthalpy. So what exactly is enthalpy? Okay, so enthalpy in science we represent as a capital H. Okay, and delta or enthalpy is the total kinetic and potential energy of a system at a constant pressure. So remember we said it has to be at a constant pressure so that we can kind of forget about that or make that one definition. Let's say that. Okay, so the change in enthalpy, delta H, is essentially a change in heat of the system. Okay, so delta H is equal to H final minus H initial. Okay, and this definition, remember we said essentially we can use heat, the temperature, to measure the energy of something. So that comes back to enthalpy, which is the total energy of a system, okay, which is essentially the heat of the system. Okay, so delta H is equal to H final minus H initial. So this is how you calculate your delta. So it's always going to be final minus initial. Okay, this is called a state function. We'll get to that in just a second. Okay, so in other words, when we're talking about chemical equations, what is our final? Our final is our products. Okay, what is our initial? Our initial is our reactants. So delta H is equal to H of the products minus H of the reactants. Okay, and the units for enthalpy are going to be joules or kilojoules per mole. Okay, you'll see this a lot, kg over mole. And that's because usually simple, like just joules will be too small. Okay, so you'll usually convert them to kilojoules because it makes more sense. So it's better to have 500 kilojoules than 500,000 joules. It just is a little bit easier to deal with. Okay. So we said delta H is the change and heat content of the system. Okay, so we said delta H again is equal to H final minus H initial. So don't forget that it's final minus initial. So basically we're interested in where do we come from and where do we get to. Okay, so enthalpy is the thermophysical property of matter. Okay, in other words, it deals with the heat and the energy of matter. So it's extensive and it's independent of pathway. We call this a state function. Okay, so a state function is independent of pathway. So we only care about the initial and the final positions. We only care about where do we come from and where do we end up. So we call it a state function. What exactly is a state function? Okay, so a state function only depends on where you started and where you ended. Okay, so I think this is a really good analogy. Okay, so we can look at two paths up the top of this mountain. Okay, so we have the first path. So let's say path B. I know they're labeled path A and path B, but I'm going to start with path B. So path B says, if I just go straight up the mountain, it's 5 miles to get to the top. And my change in elevation is from 0 to 10,000. Okay, in other words, my change in elevation is 10,000 feet. Okay, so that's one way to get there. Okay, my second way to get there, and this is the way maybe if you were hiking or driving a car even, is to wind my way. Wind up the mountain. And this pathway takes 12 miles. But at the top of the mountain, I've still only changed an elevation of 10,000 feet. Okay, so this is an analogy to what a state function is. So a state function, we only care about the fact that so if I was to say, I don't know, delta A, delta altitude. So I've changed altitude 10,000 feet. I don't care if it took me 12 miles to get there or 5 miles to get there. All I care about is how much did I change. Okay, so that's what we're talking about when we talk about state functions, and that's what we talk about when we talk about calculating a delta. So the pathway doesn't matter. We just care about where do we end up and where do we start. Okay. So I just like to go over that definition because it's something that you may not have heard previously, and I don't like the teachers throwing out the words state function, maybe you're confused. Okay, so hopefully we're all on the same page now. Okay, so there's some more terminology here. So chemists look at how energy flows between the system and its surroundings. Okay, so we're going to define a few things here. So the first thing we'll define is the system. The system, generally speaking, is the object or phase of matter that's under study. Okay, so we have an abstract definition here, and we have more of a practical definition. So the practical definition, I think it's easier to start from the practical definition, will be that if you were, for instance, boiling a beaker of water. Okay, so the water inside of the beaker, or maybe we're measuring, let's say that we're measuring the change in temperature of the water. Okay, so the water is the system. Okay, it's what we're studying. Okay, the surroundings are everything outside the system. Okay, so the surroundings would be something like your hot plate maybe that you're using. It would include the classroom. It include everything outside of the system. Okay, and notice that we have a boundary between. So you can imagine having, hot plate here. Okay, then we have a boundary dividing them. So that's kind of where the phase comes in. Because if we had a phase difference, we could also consider that a boundary. Let's not go there though. Okay. Okay, so the surroundings, again, are everything outside of the system. And the universe contains both the system and the surroundings. Okay, so here we have this sort of a brown oval that represents the system. Then we have some sort of boundary. And then everything outside the system is the surroundings. But they're both contained inside of the universe. Okay, so they're both contained in the universe. And right now their universe is this PowerPoint slide, right? But this could be something like a calorimeter, or it could be like the analogy I made, measuring the temperature of water. Okay, but just understand that both the system and the surroundings live in the universe. The system is what you're studying. The surroundings are everything else. And just as a mathematical definition, the universe is equal to the surroundings plus the system. Okay. And we'll come back to a lot of this in a little bit. So right now, we're just sort of setting up where we're going. Okay, so a couple things here. Exothermic and endothermic. Okay, so an exothermic reaction is one that gives off heat. In other words, you do a reaction and it heats up. In other words, it's hotter than the surroundings. So if something gives off heat, then it's exothermic. Okay, and remember we're talking about enthalpy here, delta H. So if something cools down, or in other words, it takes heat from the surroundings, then it's endothermic. Okay, so exothermic gives off heat, endothermic cools down, in other words, takes heat from the surroundings. Okay, and we have some mathematical applications to this. So when energy leaves the system and flows to the surrounding, the energy of the system decreases. Okay, so to designate this flow of energy, a negative sign is used for delta H. So specifically what we're saying here, in other words, the sign of delta H will be negative. And a lot of times, if you haven't seen this before, a lot of times we'll put parentheses around a minus sign or negative sign to remind us that it's there. Okay, so in case if I was to say minus a minus, I might put parentheses there. Okay, so a minus delta H is exothermic. Okay, so minus delta H, exothermic. In other words, it's something that will give off heat. Okay, so energy leaves the system and goes into the surrounding. Then we have an exothermic reaction. Okay, so we have heat leaving the system into the surroundings. So essentially, the energy of the system goes down, while the energy of the surroundings goes up. So the energy of the system goes down, but the energy of the surroundings go up. That's why it's negative. Remember that we're talking about this from the point of view of the system. So according to the system, it's losing heat. According to surroundings, they're gaining heat. But the system is losing heat. Okay, and the opposite is true as well. So now we have endothermic. Okay, so when energy enters the system from the surroundings, the energy of the system increases.